Es Mimic, en el que pues estamos capacitando a diferentes maestros, maestras y personal de las diferentes escuelas, sobre todo los CECITs y el CDA, para participar en este proyecto de divulgación que es el armado y puesta en marcha de un modelo a escala de la Estación Espacial Internacional que está diseñado por diferentes personas que han colaborado directamente en la creación de esta nave espacial, este laboratorio en órbita que está a 400 kilómetros en órbita alrededor de nuestro planeta y con el objetivo de poder acercar la ciencia y la tecnología espacial a las alumnas y los alumnos del Instituto Politécnico Nacional y el público en general. En esta ocasión tenemos la presencia de Samuel Treadgold. I hope I'm saying it right. Y la conferencia se titula Science, Science from Space, Real World Telemetry o Ciencia desde el espacio, la telemetría del mundo real. Y bueno, les cuento un poquito de Sam. Sam es ingeniero del equipo de análisis de riesgos de meteoroides y desechos orbitales de la NASA y lleva 11 años realizando tareas de programación y diseño asistido por computadora en el proyecto MIMIC de la Estación Espacial. So, Sam, thank you very much for being here with everyone here at the National Polytechnic Institute of Mexico. And I don't know, Javier, do you want to say something else about this conference or we just go ahead with Sam?
Okay, just a couple of minutes that we're very, very happy. Sam, thank you so much. Gracias a todos por reunirse. Esa es nuestra tercera conferencia de las 4 series que vamos a tener. En nuestra siguiente semana damos por concluida la serie de conferencias, inspirando con las comunidades. Cómo poder adaptar este proyecto para hacer un impacto en nuestra sociedad.
Genial. Muchas gracias, Javier. So, Sam, if you want to go ahead and start.
All right, sure. Let me see if I can share my screen. Sure, I can figure out how to do that. There we go. Okay, can you see what I have up on my screen?
Yeah.
All right. So hi, my name is Sam Treadgold. I'll be talking about the telemetry from the International Space Station, specifically the public telemetry that we use on the ISS Mimic project. And so firstly, what is telemetry? Telemetry is any data that gets collected remotely that includes everything from the health of the astronauts to how many computers are connected to what the solar panels are doing to the battery levels to the spacewalkers to the antennas to everything. All the data coming down from the ISS is just called telemetry, and it is what gets sent to mission control to let them know that how the space station is doing. This is a screenshot of one of our telemetry pages showing all of the public telemetry from the ISS. And I just wanted to note that we have roughly 300 telemetry values here, but the actual ISS full telemetry contains over 100,000. This is just a small subset of all of the data coming down from the ISS 24/7. So the public telemetry covers life support, power, navigation, robotics, communication systems, and so much more. And we are trying to incorporate as much of it as possible in our Mimic telemetry screens. And so far, I think we've done a pretty good job, but we still have a lot of data to cover. But I'll go over what we have so far. So firstly, this is I love showing this chart. This is the convoluted path that the telemetry takes to get from the International Space Station to all of us on the World Wide Web. So it, originates on the space station. It gets beamed up to satellites very, very high above Earth called TDRS. The TDRS satellites send it back down to Earth to either New Mexico or the island of Guam. From both of those sites, it comes back to NASA Johnson Space Center, where you might think its journey ends, but it keeps going to Italy, where there's a company that NASA has contracted with to kind of package the data up nicely to show to everyone around the world. So from Italy, it gets sent out to the World Wide Web. And so it takes a very, very long journey to get to us. But that's, I think, one of the neatest things about the telemetry is just how many systems it has to travel through to get to us. But yeah. So why is the telemetry important? So the telemetry is critical for us on the ground, for mission controllers, for engineers, for everyone to be able to see the value of exactly what is happening on the space station. So they can see when problems will occur before they happen. So for instance, a mission control can constantly monitor the oxygen levels and can determine if there is, a leak or a problem with the oxygen generation systems before it becomes a problem for the astronauts. So that's why telemetry is important to NASA. But then for us on the Mimic team, it's important because it's what lets us connect everything to what is actually happening in space and to bring all of these remote data systems to the general public. So these are the 4 main systems that the ISS Mimic telemetry focuses on. So the solar rays, these large rectangular power generating features here. The radiators, which are these smaller white rectangles here. The robotics system, which is this kind of train car thing that goes all along the front of the space station. And the outboard truss, which kind of connects all of the power and heat rejection systems together. So focusing on power, the solar rays are one of the most important features of the International Space Station because solar power is the only energy available to the space station. So it's just one of the most critical systems that the ISS needs to be able to charge its batteries every single orbit, 16 times a day, and then discharge them and power all of the systems on the space station that keeps the crew happy, healthy, and alive. So this is our electrical power systems screen. EPS is what the acronym refers to. So this depicts the status of each of the 8 solar array wings on the space station. So we can see the voltage, we can see the angle of the solar rays because each of these solar rays individually rotates to track the sun. And I have current here. The current is not working, unfortunately, but we used to be able to tell the total power used by the ISS, which I'm hopeful that will resume again at some point. Communications is my favorite subsystem. So these are, in this picture, you can see 3 antennas. These 2 right here, and then this one off to the side on the left side screen. So the antennas are what, send all of the telemetry back to Earth. So you can tell the thing I always point out is that the antennas are on the top of the space station, whereas you might think they would be on the bottom of the space station to send the data back down to the ground. But the ISS is actually traveling too fast to send the data back directly down to the ground. So as I showed in that chart earlier, it sends the data way up high to these satellites that are way, way, way above the ISS altitude. And they're so high that they're moving pretty slowly relative to the surface of the Earth. So you can see this antenna is kind of tilted differently than this one. That means this is the active antenna, and it's the one that is tracking those satellites to send all that data back home. So this is our CNT screen. CNT stands for Command and Telemetry. So of the 6 primary antennas on the ISS, this screen tells which ones are active and which ones are not. So there are 2 of these antennas in the middle called SGANT, which stands for Space to Ground Antenna, which I mentioned earlier does not send the data directly to the ground. So it's kind of a misnomer, but the data gets to the ground eventually. These two outboard ones are called SASs, S-band antenna subassemblies. And then these antennas scattered about are UHF antennas. So the two antennas on the middle send all the like video data from the space station and all of the payloads. So all the science data comes over these antennas. The SASAs send all of the critical telemetry. So what all the subsystems are doing and health information and all the solar array stuff. So all the information that we use on Mimic comes from the SASAs. And then the UHF antennas are for communicating between the ISS and any astronauts who are on spacewalks. So those are typically only active during a spacewalk. So it's pretty cool to see them light up whenever they're talking to the astronauts. So this is the KU band, the SGANT antenna page. So it shows which satellite the ISS is talking to and the elevation angle of the KU band antenna. So it shows which direction the antennas are facing to communicate with the satellites. This is the SASA screen for the S-band antenna subassembly. This is my favorite antenna. If you know, not that you have to have a favorite antenna, but this is mine. So there are two of these antennas, and as I said, they're very important antennas. So one of them is active always, and then the other one is kept as a reserve, and they trade off about 4 times a year. So the screen shows which SASA is active, and it shows their statuses. For some reason, they give the status as not off instead of on. There's a lot of engineering discussion behind why that is, but I won't go into that. And then, of course, it tells you where the antenna is pointing, so we can also track which satellite it's talking to. And this is the screen for the UHF antenna. So again, these are only powered on when they're talking to the astronauts. Okay, we also have a kind of general ISS info screen, which shows you how fast the ISS is moving, its current altitude, and its current mass. So typically, the ISS is moving around 7.66 kilometers per second, which is just the orbital velocity at its altitude. So that speed rarely changes. And then altitude, 425 kilometers, is roughly the altitude that the ISS stays around. It varies between like 410 and 425-ish. And then the interesting number on this screen, in my opinion, is the station mode and the total mass. So the total mass is the actual estimated exact mass of the space station. So almost 500,000 kilograms. So the interesting thing here is that when a new vehicle docks to the ISS, like a cargo mission, this number will increase by whatever the amount of mass that the cargo mission is bringing up. So I like watching that during vehicle dockings. And then the station mode is an interesting one. There are a bunch of different modes that the ISS operates in. So the mission control can put it's typically standard mode when they're just doing normal operations, but it can enter proximity operations when there's a spacecraft coming off to drop off supplies or new crew. External operations when there's a spacewalk happening or some robotic ops. There's reboost mode, and it's interesting to see exactly what the ISS current operating scheme is. So it usually just hangs out in standard mode, which means all of the equipment is active. And I don't remember exactly what all of the modes do, but they change the configuration of the equipment to be ideal for whatever is happening at that time. So the thermal systems, these giant white radiators, the largest radiators ever sent to space, are what control the heat rejection for the space station. The big 3-section radiator on the right is responsible for the heat rejection for the crew modules, so where the astronauts live. And then the one on the left is responsible for just the solar rays. So then on our thermal control screen, you can see both the flow rate of the coolant in these radiators, as well as the pressure and the temperature. So the radiators use ammonia rather than like water, because water could get too cold and freeze in the lines. And then, expanding frozen water could crack the lines and it could leak and just ruin everything. So they use ammonia, which has other problems because it's toxic. So it needs to avoid getting ammonia inside the crew modules, which is always a concern. But it's interesting to see the radiators change, and the radiators actually rotate to kind of optimize heat rejection. They used to go in this auto track mode, so you could see the radiators actually move around a lot, but now they pretty much just leave them in these positions on the screen. So they typically don't move around, but it is interesting when they do. For navigation, I have a picture of these four, they call them CMGs on the ISS, control moment gyroscopes. These are huge, multi-100-pound metal discs inside here that spin up very fast in order to use angular momentum to kind of steer the ISS.
Recording in progress.
So the ISS also has a bunch of thrusters on it to be able to steer. But the interesting thing about the CMGs is that it uses only electricity. So whenever possible, they like to use these CMGs to steer the ISS so that they don't consume fuel on board, which is, a limited commodity. So on this screen, you can see way too much information about the CMGs. It's surprising how much telemetry they just throw out to the public. So you can see the temperature and the current and vibration and the speed of every single one of the CMGs. So the CMGs typically all operate around the same speed, 6,600 rotations per minute. So they are really going fast. And so they don't spin them up or down to change the angular momentum. They just turn them to kind of change the momentum vector to whatever cancels out the ISS torques. So you can see here in the middle is the most interesting part of this screen. It's the saturation percentage. So right now in this screen, they're at 10% saturation because there's only so much angular momentum that can be electrically maneuvered for the ISS before it's just overwhelmed by the natural torque environment. So when this number gets up to, I think I've seen it around 70%, the ISS has to do what's called a desaturation maneuver. So it will actually fire the thrusters to kind of cancel out whatever the CMGs are doing. So it kind of resets them. So this screen's always interesting to watch if you see the saturation getting high. Of course, another very critical aspect of the space station telemetry is the ECLSS system, which is the environmental control and life support systems. So from this screen, we can see the cabin temperature, cabin pressure, airlock pressure, crew lock pressure, wastewater tank percentages, oxygen states. So we can see basically cabin pressure should always be roughly this value, 754 torr. That's pretty much just standard 1 atmosphere pressure. This number changing is pretty much a bad thing. Crew lock pressure is in the airlock. So if this number decreases, that means hopefully, their crew is about to go on a spacewalk. So that's always interesting to see. We can also see, of course, on this screen, we can see the quantity of urine in the wastewater tank. So you can tell when the urine tank is being filled up, which is, always fun to see. And we can also see the internal active thermal control. So this is the thermal regulating systems of the inboard systems. So these are the thermal control systems that use water for coolant, because I mentioned that ammonia is used on the outside. But on the inside, ammonia is toxic, so they'd be worried about exposing that to the crew, so they use water. And we can also see how much oxygen is being generated and, which it's typically more than enough to keep the crew comfortable. But there have been times where we actually noticed there are always a couple of small leaks on the ISS, and we've been able to record that just with the public telemetry, which is interesting to watch. So EVA, or extravehicular activities, also known as spacewalks, are one of the key features of the ISS because the crew constantly has to go outside to repair systems, install new science experiments, or upgrade the space station. So it's cool being able to, get a glimpse into what is required to prep for an EVA. And so we have these spacewalking screens. There are 2 airlocks on the space station that support spacewalks. So there's a US airlock and a Russian airlock. So the Russian astronauts have their own spacesuits that they go out there. Airlock up here, MRM-1, and then the US astronauts come out of the Quest airlock here. And unfortunately, there is no public telemetry for the Russian EVAs. So can't add that for now. But on the US side, of course, as I mentioned before, we can see both the airlock pressure and the crew lock pressure. It's confusing, but the airlock refers to the inner part that's always connected to the main space station. So the airlock is normal pressure always, ideally. And then the crew lock is the isolated segment that gets pumped down to vacuum for spacewalks. So on this page, it says airlock pressure. I get that's confusing. That should be crew lock pressure. But so we can see on this needle gauge, we can actually watch the pressure in the crew lock drop to roughly 0. And when that happens, we can see the leak check begin, and we can see when they're actually about to go out the door on a spacewalk, which is always fun. There's actually a lot of information on charging all of the batteries and power systems for the spacesuits. So that is displayed on this screen, which of course is interesting to watch during a spacewalk. And then the screen also kind of gives an overview of the different sections of a spacesuit. As I said, no telemetry for the Russian EVA screen, but hopefully we can find something to add there at some point. And okay, this screen details the exact orbital parameters of the space station. So this screen is mostly just exciting because it tells you when the ISS is going to fly over your location. I like it though because it also shows where the communication satellites that I was talking about earlier, the TDRS satellites, where their orbits are, and they'll light up when we have data for which satellite the ISS is talking to. The screen also predicts the next time ISS is going to fly over your location and gives some more information, the same altitude information. The orbital inclination and period is how long it takes to go around the Earth. So right now it takes ISS just over 90 minutes to complete a full rotation around the Earth. And the screen also shows the total number of times ISS has ever gone around the Earth, which as the time of this screenshot, actually a couple months ago, we just passed 150,000 Earth orbits, which I think is pretty cool. Also have way too much information about where to look in the sky for upcoming ISS pass, as well as the raw, just everything you could want to know about the true orbital values of the ISS. So this is the more complicated stuff, but the state vectors and the actual orbital elements for the ISS, which I just like looking at. The robotics systems for the ISS is, in my opinion, the Canada arm here, also called the SSRMS, the Space Station Robotic Manipulation System. I think this is probably the most important system on the ISS, aside from life support. This arm can kind of inchworm. It can ride on this train car all over the space station, but it can also detach from it and inchworm all over the space station on its own. And it can carry, 100-pound payloads. It can attach new modules. This is the workhorse. This is the thing that built the space station. And I love it when it moves. So we can see telemetry for that train car I said that it moves on, which is called the MT and the MBS. And we can see the telemetry for the SPDM, which is its little, the hand, they call it dexter, which attaches to the arm. And of course, for the arm telemetry. So we can see exactly where on the ISS that train car is currently located. We can see what it's moving. We can see its speed, which it typically moves at a maximum speed of 2.5 centimeters per second. So it's, not blazing fast, but I like watching it travel along the space station regardless. And then for the arm is a 7 degree of freedom robotic arm. So we can see the current motor angles for each of those 7 joints. And we would like to, there is a website using this telemetry that actually renders an animation of the arm using whatever its live position is, which is something I'd like to include in Mimic, which is, it's pretty cool watching it move though. It does not move very fast. Everything in space, they like to move very slowly so that you have a much lower chance of breaking something. And similarly to the arm, the hand called dexter, the SPDM, I'm gonna say it, the special purpose dexterous manipulator. I'm never gonna say that again. The SPDM has 2 of its own mini arms, which are each also 7 degree of freedom robotic arms. So this is for very, very precise, controlled stuff like changing out really tiny parts, like little electronics boxes all over the space station. And this thing gets its work done. Like it is one of the most, like the robotic system is absolute masterpiece. We have a telemetry screen for the USOS, which is the United States Orbital Segment, which is basically the front half of the space station. On the front half of the space station, there are 4 docking or berthing ports. There are 2 docking ports and there are 2 berthing ports. And this is needlessly complicated, but berthing is where the space station or the spacecraft can't attach itself to the space station. So it has to be grabbed by my favorite thing, the Canadarm, and attached directly to one of these ports. The good thing about berthing is that the ports are really, really big, so they can fit huge pieces of equipment through them. The docking ports, however, have equipment that helps the spacecraft automatically guide themselves to docking, so they can do it without any human control and just do it completely autonomously. So in this picture, there are 3 spacecraft attached. We've got 2 SpaceX Dragons, of course. One is a cargo dragon, one is a crew dragon, and then we have a Northrop Grumman Cygnus cargo vehicle here. So there are 3 of the 4. This is not live, but when I took this screenshot, there were 3 vehicles attached to the ISS on the US side. So whenever the vehicle attaches to the ISS or detaches, this page should update almost live. Similarly to that, the visiting vehicles page shows the all 8 of the docking or berthing ports on the ISS. So there are 4 on the US side, 4 on the Russian side. The Russian side, they're all docking ports though. So there is, of course, a Russian specific side, which shows the 4 docking ports. Those are all going to be either Progress or Soyuz vehicles. Soyuz is the Russian crewed vehicle, and Progress is the Russian cargo vehicle. There is a crew screen, of course. This is not technically telemetry, but it is, information about who's on the ISS. So the crew screen will tell you how many astronauts and who is currently on board, what country they're from, how many days they've spent in space. And of course, my favorite thing about this screen is just this counter in the top right that shows the time that the ISS has been continuously crewed. So as of this screenshot, it was just over 24 years. As of now, it's 24 years and 6 months of continuous human presence in space. So that is just the coolest thing. Of course, it's not the same, not 24 years for these people on the screen. It is a rotating crew, but 24 years of no one of the space station never being empty, which I think is just awesome. The science screen, science is, of course, the entire purpose of the ISS. So I'm disappointed that we don't have that much to show about exactly which experiments are on the ISS. We are definitely working on that though, because there are hundreds and hundreds of experiments that are currently on the ISS, and they are being done for all branches of science, and it is just some incredibly important work that we really should show off. But we can at least show all of the different science facilities on the outside of the space station. All of these little pallets on the outside, they're called ELCs, Express Logistics Carriers. Express is also an acronym. I don't immediately remember what that stands for, but yeah, acronyms go crazy. So this section here, I don't know if y'all can actually see the mouse. I hope so, but so this is called the Japanese Exposed Facility. This is also called the front porch of the ISS. So it's this little platform outside for science experiments to be able to either measure the Earth or interact directly with the space environment. And it's just cool. And there's a European one over here also, as well as on the left side of the image, more external palettes and AMS, which is one of the coolest experiments ever, the alpha magnetic spectrometer, measuring stuff from deep space neutrinos. And I think that is my last slide. So that is everything that the ISS Mimic program is currently doing with the telemetry. And I'll just conclude by saying that there is a lot more telemetry to include, and we want to use all of it. So yeah, I guess are there any questions or?
Okay, thank you, Sam. Ana, Ivy, Jorge, preguntas. Sofía.
Una pregunta. En la presentación tiene dos brazos mecánicos. Yo sabía que era solamente uno, el canadiense, pero no sé si nos podría explicar un poco más.
Okay, Sam, can you go a little bit deeper on the two arms, el Canadarm and Dexter?
Oh, great question. Yes. There are actually 4 different robotic arms on the space station. We only have telemetry for the 2. But the 4 arms are, of course, the Canadarm, SSRMS, and the SPDM. There's also called the ERA, the European Robotic Arm on the Russian segment. And then there's the Japanese robotic manipulation system. So the Japanese arm is just attached to that front porch to place payloads there. And then the European one is to help assist in building out the Russian segment.
And the Japanese,
sorry, go ahead.
The Japanese is similar to the Canadarm, right?
Very similar, but it's a lot smaller. The Canada arm has these 2, they're called latching end effectors on either side. These are the things that grab whatever they need to grab. So these have the interlocking metal rings that are meant to attach to what are called grapple fixtures. So you can see on a picture of the space station, it's just dotted in these little circular points with like a protruding antenna type thing in the middle. And those are grapple fixtures. Those are points for this to attach to. And so it can attach to one of these points and plug in electrical connectors and get power directly from the space station through any of these points. So one of these sides, Lee B or Lee A, will attach to a grapple fixture, plug in, get power, and then the other side will detach from wherever it was getting power. So it'll now be powered from the one side, and it'll repeat the process, and it'll just go end over end until it gets to wherever it needs to go. And watching them very slowly move it all over the space station is wild.
Thank you, Sam.
Thank you.
Sofía.
Thank you. I wanted to know, what is the most common risk factor detected through telemetry? for an astronaut living on the ISS?
Oh, that's a great question. I don't immediately know the answer to that. Right now, there's a problem at the back of the Russian segment where the module has just withstained so many dynamic events that there are cracks propagating through it. So their station was losing a lot of its air every day through these cracks in the back of the space station. So right now they just kind of close the hatch and they put, crack sealant all over it, but losing air through this segment is currently the number one risk on the space station. So they try to just keep that module closed as often as possible. That module the problem is though, it's this module here on the service module, Zvezda. The problem is that this is one of the docking ports, one of the 4 docking ports for the Russian side, and it's the most commonly used one for cargo modules. It's a very important docking port because at the very back of the space station, it also provides the thrust directly through the whole space station. So this port is most useful for reboosts. So that's why Russia doesn't want to close off this port. So that's just one of the risks they have to manage is, worrying about oxygen leaks.
Okay, and well, you show us a panel with thousands of indicators. So could you tell me, in case of simultaneous problems, how do you decide the priority of attention?
Sorry, could you repeat that?
Yeah, if you have, I don't know, 10 or 20 problems simultaneous that are present in the panel, for example, you show us a panel with thousands of indicators or thousands of values.
Mhm.
How do you decide the priority of the attention of all the problems?
That's a great question.
Mhm.
So on the screens in mission control, the problems will be segmented out by severity. So some of them will present as critical, some will just present as warnings, some as errors. And so if a problem presents as critical, it will be top of the list. And that's the one, so the system automatically kind of separates potential telemetry problems into severity. And so the mission control officers can determine themselves, just they don't have to be overwhelmed with information. They can immediately identify the number one problems. And so they'll take appropriate actions based on whatever presents in that list.
Thank you,
Thank
Sam.
you, Sam.
¿Otras preguntas en español o si gustan pueden escribirlas también?
Buenas tardes, yo tengo una pregunta. No sé si me escucha.
Adelante. No se escucha muy bien tu micrófono, no sé si es solamente en mi parte.
Sí, se escucha bajo y un poco ruidoso.
Ajá.
It's from here. Good afternoon, Mr. Treadgold. I've got a question for you. What kind of information are you going to use for this educational program? I mean, all of this information is for you?
¿Escuchaste, Ana, la pregunta? No se escuchó muy bien. ¿O la puedes escribir, Sergio, en el chat?
Yep. One second.
Mientras le escribe, ¿alguna otra pregunta?
Yo quisiera hacer una pregunta.
Adelante.
De toda la información que se presentó en la primera lámina, que entiendo que es toda la telemetría de la Estación Espacial Internacional, ¿cómo podríamos reconocer de qué parte a qué parte habla de un tema y de qué parte a qué parte habla de otro tema? ¿Hay encabezados? ¿Hay segmentos de información? ¿Se envían por por grupos independientes.
¿Te refieres a eso que estamos viendo ahorita?
Exactamente, o sea, por
Ajá.
ejemplo, la plática muy interesante, por cierto, estaba hablando de la información, por ejemplo, del oxígeno que existe dentro de la Estación Espacial Internacional y después también incluye la información de dónde está ubicado el robot y después incluye información pues de muchos temas que son requeridos en el tiempo normal de vida de la estación espacial, en el día a día. Pero aquí en la lámina, pues, ¿cómo sabes qué de estos datos conforman la información del hábitat interior? ¿Qué de esta información conforma el lugar en donde la estación espacial está en este momento con respecto a la Tierra? ¿Qué de estos datos conforman cómo están orientados los paneles? Y seguramente hay 100 temas distintos al respecto.
Okay, Sam, the question is on the uh, website that you just showed. Can you go back? Yes. Okay, so asking if how do you know and determine based on those values which are the ones that are related to any of the topics that you talk about, like the Dexter, the rotors, the solar panels. How do you know which of these is related to any of the?
This screen, we have two telemetry screens. This is called the dashboard. This one, the values are colored based on their subsystem. So all of the red values are related to the robotic system. All of the light blue values are related to the communication system. All of the brown values are related to navigation. This one is more confusing though because it uses the actual name of the telemetry. So CCMDM2, which is not useful, and you have to mouse over it and then it kind of expands. But there's also the ISS Mimic, this page, which is more plain text, I think. So this one on the left-hand side shows the category. So this shows all of the spacewalking, all of the power, all of the Russian telemetry. So yeah, there are the two different options, and one of them is just color coded, and the other actually has the text. Active thermal control. So this is the thermal
All right, thanks so
regulating
much.
systems of the inboard system. So these are the thermal control systems that use water for coolant. Because I mentioned that ammonia is used on the
What is that,
outside,
Sam?
but on the inside,
I was
ammonia
hoping
is
to
toxic, so they'd
show
be worried about
the
exposing that to
videos
the
of
crew,
the
so they use
ISS
water.
right now, but it is
And we
in
can
the
also see
nighttime,
how
and
much
it's about to enter the
oxygen
region of the
thermal
world
control
where it
systems
doesn't
that
get
use
telemetry
water
for
for coolant.
signals. So
Because I
it's
mentioned that
not
ammonia is used on the
useful.
What is that,
outside,
Sam?
but on the
Not
inside,
good.
I was
I mean,
hoping
ammonia is
to
toxic, so
show
they'd be worried about
the
exposing that to the
videos
crew,
of the
so they use
ISS
water.
right now, but it is
And we
in
can
the
also see
nighttime,
how
and it's about
much
to enter the
There's a
oxygen
couple
region
of
of the
thermal
world
control
where it
systems
doesn't
that
here
get
use water for
telemetry
in the
coolant.
chat.
signals. So
Because I
it's
mentioned that
not
ammonia is used on the
useful.
what is that,
outside,
Sam?
but on the
So, did you read any of them, Javier?
No, can you read them, Anna?
Sí. First one is from Fabiola, and it says, we can clearly see that we have many different dashboards to show the status of different variables. Do you have something additional to perform maintenance?
That is predictive.
Something additional, maybe if I understand, something that predicts that something needs maintenance, like not already having issues, but that will eventually.
There was an interesting situation that happened one day when we were presenting the ISS telemetry to a group in Italy. And we were showing this screen right here, the EPS, the electrical power systems screen, which shows all of the solar rays, and it shows them collecting sunlight and charging the batteries. And in the middle of our presentation, one of the solar rays turned off, and it actually got a big red X through it. And unbeknownst to us, that solar array had just failed completely. And somebody in the chat in Italy actually brought that up and said, "Is something wrong? Is everything okay?" And well, I don't remember what we said at the time, but we didn't know, but something had just catastrophically failed. It was a sequential shunt unit at the base of the solar array, which is responsible for kind of collecting. It's like a giant diode for the solar array. And it had actually failed, and the entire solar array turned off, and the station lost 1/8 of its total power in just a few seconds. So that time, we couldn't have predicted that something was about to fail. Sometimes stuff just breaks immediately, but it was interesting to see that failure happen in real time. Otherwise, the indicators that something is about to fail, especially say on the CMGs, this vibration level here and the temperatures, if these exceed a certain performance threshold, if the vibration gets too high, it's a good chance, the higher vibration on something on a giant metal disc rotating at 6,600 RPM, if the vibration gets too high, there's a good chance that it's going to fail imminently. So then they can take corrective actions to either decrease it to extend its life or have the astronauts go and replace it. Those are just two examples.
Okay, Sergio, who had the problem with the microphone, he was asking what kind of information are we going to use for this program?
In what regard?
It's not very clear on that, but I think
for the mimic.
For the mimic.
Well, on Mimic, this is all within the Mimic program. Relative to the actual rotating models that are attached, it primarily uses these angles, the starboard Sarge angle and the port Sarge angle, and then the angles for the solar arrays. So this is the most important information for just the Mimic model, I would say.
And the one that you can see.
Mm-hmm.
Mm-hmm. All right. Have you incorporated method for analysis AI on data? It says since it is an international, oh no, that's the questions. So one, if you have used AI to analyze data, and if this is an international project, standardization is important. And what kind of standards of quality or you use to make sure the new models are executing changes and reparations in the equipments?
So yes, I have used AI for analyzing the data. In what was I didn't know that it was capable of this, but I was working on the screen for the Russian visiting vehicles. Actually, I'll bring up the telemetry list. So here, there's a bunch of Russian data. So such as distance from service module, rate from service module, KERS P test mode. KERS is the Russian antenna that talks to their vehicles. Capture signal availability, target acquisition signal, functional mode signal, standby signal, docking flag. So all of these different telemetry values tie into when a Russian vehicle is docking or is beginning its approach to the ISS. So starting several orbits out, the vehicle will start talking to the ISS and trying to determine its location and how quickly it needs to approach it. And all of this data was a little overwhelming for me. So I actually just fed it all to ChatGPT. I gave it the entire Russian telemetry data for 6 hours. And I said, tell me any data correlations that you can find. And it responded with a list of it. It said, capture signal happens at this distance from the ISS. The rate changes to here when it approaches the final orbit phasing burn of the ISS. The docking flag occurs here, this occurs here, and these mean this. And that was the most impressed I've ever been with ChatGPT, to be honest. So I've used it a little bit to determine correlations between different data.
And do you know about any standards? Probably like certificate of quality, like ISO 900, something like that, that you use in the modules. So whenever they attach to each other, can be repaired.
Yeah, so that I don't I don't know if they follow any ISO standards or not, but they develop an interface control document. And they say if you're building a module for the ISS, this is what it must dock to. This must be the diameter. This is what can fly. This is the mass that can fly. This is how the electrical system works. So basically, NASA controls that standard. And any international partners, they will get this document and they'll work with NASA to make sure that their module can plug into the ISS.
Perfect. And there's another question. This is a question from a social network. What could be the future opportunities in the telemetry field?
Oh, for me, I want to encourage more some of the new space stations, especially the lunar space station, to follow in the footsteps of the ISS Live project, which released all this data to the public. So I want more space telemetry to be made available to the public, not just so that we can make models of it that spin solar rays and stuff, but also just because I think it's more interesting to see all of this data that goes into space architecture engineering. So you can see exactly how much the life support is having to work and how much power is required, and I think that's the most important thing to help us moving forward is kind of just transparency in telemetry for space vehicles personally. But
Okay, and we have a last question from Fabiola. She says that this data talks about the status of variables that are from the space station, but she wants to know if from space station you take data from Earth.
So that's part of payload data rather than telemetry, which is kind of an arbitrary distinction. But the ISS has several experiments that are Earth science based. So on that, the Japanese segment that I mentioned, especially this one on the front porch, as we call it, it has several experiments that measure the ocean, and they measure formation of ocean currents, and they're used for I assume weather analysis and measuring how the oceans are changing. But yeah, so there are a lot of kind of downward pointing experiments that test not only laser communications with Earth, but also just measuring, especially the oceans, but also farmland variability and like forestation changes. So for instance, the not even just experiments, but whenever the crew takes a picture of the Earth, as they always do, they're always hanging out the windows and taking pictures. But then those images are downlinked to the image analysis team, and they use AI to kind of stitch the images together and to form maps over time of how like forest levels are changing across the whole world. So there's a lot of connection to Earth science just from the space station, especially.
Okay, thank you, Sam. I think that concludes our Q&A session, and also this session as well. I don't know, Anna, do you have something to close?
No, I think we're good. Inge, ¿a usted le gustaría decir algo para cerrar?
Pues lo mismo de hace 8 días y de hace 15 días, agradecerles el apoyo y la orientación que nos dan para entender mejor el proyecto y conocer mejor la estación espacial. Muchas gracias.
Okay. Sam, he was telling that he's very grateful that you're showing your work related to the space station, so we know more about it.
Oh, thank you. My pleasure.
Okay, Ana, well, thank you so much. ¿Algo más, Ana?
Nada más, gracias a todos. Recordarles que la próxima semana tenemos la última sesión con uno de los maestros que, bueno, ya vimos un poco la manufactura, vimos un poco de dónde surgió la idea con Brian, cómo nuestras dudas sobre la impresión, los calibrajes y todo esto, y la manufactura. Hoy conocimos más sobre la telemetría que se usa para conectarla con la estación. Y la próxima semana finalmente vamos a conocer la experiencia de un maestro como nosotros que ha hecho el proyecto, lo ha aplicado en Brasil específicamente y nos va a contar pues cómo le fue ya directamente con los alumnos y cómo lo ha pues compartido. Entonces pues creo que esto va a redondear muy bien todo lo que tenemos que hacer. Y pues seguimos ahí pendientes de lo que necesiten para completar el curso y para que finalmente nos podamos ver allá en Houston y armar nuestras mimics. Muchas gracias a todas y todos. Muchas gracias, Javier. Eres lo máximo. Gracias a todas y a todos.
Gracias. Nos vemos en la siguiente plática la próxima semana.
Thank you,
Gracias.
teachers,
Hasta luego.
Javier, Sam, Cristina. Thank you.
Bye. Thank you, Sam.